What I saw some slideshow that my sister had made about solar power, and basically solar power is nuclear power, but the reactor is in an appropriate place, right? It's far, far from the Earth, so it's all the harmful radiation is filtered by the atmosphere, and we don't have to worry about the nuclear waste of it, right? At least not for a few billion years, right? All right. Now let's just look at the simplest. I'm going to go from simplest to most complex solar power utilization, right? The simplest is just what we have going on at our house. We've got this giant overhang. We face south. In the summer, the sun is high up, so it doesn't shine in our house. But in the winter, the sun does shine through that window and warm up our house. And then, of course, if you put like a heat-absorbing surface and have no furniture, you're all set, right? Okay. You can be a little more complex about passive solar, and passive just means it's nothing, no moving parts really. Um, we had at the camp I worked at, we had this going on. Basically, they have a large thermal mass, and in this case, it was a fireplace, a giant stone fireplace. There was a big window there, and the sunlight would shine in the winter, heat up that warm up that giant chimney. And then all night long, that chimney would sit there and release energy. It would kind of warm the surface there. Of course, in the summer, you kind of don't want that going on. And that was the problem with what they built up at camp, was that they didn't have any way to keep the sun from getting in the summer. And boy, that place got kind of warm in the summer. But in the winter, it was really nice. So you just need a shield or something like that in the summer. Now, if you're going to heat water or something like that, or air, there's lots of options. I just put this on here because a friend of mine this is the simplest thing, right? This is just a black piece of PVC pipe with water in it. And a friend of mine did this. He stuck this up on his roof. He's got a little valve and a hose and a little, like you could even just use a sprinkler head or something like that, right? A shower head. And he just showers on his back deck. This is a camp shower. What you can't see is the other side of it's clear, and this is black plastic. You fill it with water, leave it in the sun, it warms up. Okay, this is somewhat more sophisticated. So that's a water storage tank. There's a pump in here, and it pumps the water through these panels, which are oriented at the sun. The same idea here. We've got a tank inside a box. This is reflective. This thing is painted black. And I've heard, but I haven't found pictures of it, that in the Middle East, it's so hot and sunny that people take old telephone booths and put the water tank from an old water heater, paint it black, and stick it in the booth. Take the phone out, I suppose, right? But just a black tank inside a booth like that generates all the hot water you need. And I've actually found one of these on trail when I was a canoe counselor, and the kids just loved it. Just a hot shower on trail is like the biggest luxury. Here's a system where they've got a panel that collects solar energy, and then we just blow air through it. It's got some moving parts, but it's a bit more efficient. Okay, so just the idea that the energy from the sun can just heat up water or air directly. That's actually, if you're heating, if you want to heat water, that's the most efficient way, really. If you're using photovoltaics, those are so inefficient. Okay. So, but let's, obviously the problems I see on the IB tests tend to have to do with photovoltaics. So we'll get there in a sec here. I just wanted to show a picture of this. This is the Four Solaire, which just is French for solar furnace, right? This is where the high temperature, so this is a giant concentrator. It's a parabolic mirror that concentrates all the sun energy on this little spot there. So that's super, super high temperature. These things are heliostats. So when you want to use this facility, you get it all set up, and then these heliostats just reflect the light into this, and it concentrates it, right? Now, what you can't see is on the back side, there are heliostats and downward-facing concave mirrors for smaller scale experiments. And I think my sister lived over there when she lived in France. But anyway, so this is it, right? This is what we put on our houses. You see water heaters on house roofs, right? But lately, what you see are people putting electrical panels on. And the thing you got to understand is that they're not terribly efficient. They're, a really efficient panel might be 25%. And they're getting more efficient, but they're never going to be terribly efficient, I don't think. But electrical energy is expensive. So these things pay off, right? If you can generate electricity and not pay your electrical bill, you could save $90 a month. Well, that's going to pay off eventually, right? Okay. Let's look at one of these problems. What we're going to do here is we're going to use intensity as power divided by area. We're going to use power as energy over time. We're going to use our efficiency. Right, and then we'll have to do a unit conversion, right? Okay. So a photovoltaic panel measures 1.75 by 1.10 and is 23% efficient. How much total electrical power can it put out if the solar intensity is 890 watts per square meter? Okay, so let's figure out the power that we're capturing with the panels, right? So from this, we know that power is going to be intensity times area. And this will be what our power input or something like that, right? So the intensity is 890 watts per square meter. And then the area of these panels, assuming they're rectangular, not rhomboid, right, is 1.75 meters by 1.10 meters. So the power input, that is the total energy of the incoming sunlight, is 890 times 1.75 times 1.1, okay? And that is 1,713.25 watts of power input, right? Now, it's only 23% efficient. So what that means is that only 23% of that becomes power output, right? So power output is efficiency times power input. I'm just using, I guess, this thing here, right? Okay, so 23%, so 0.23 times 1,713.25. So I take the number on my calculator, go times 0.23, and I get 394.0475 watts. Okay, so that's our first answer, right? Is how much total electrical power can it put out, and that's our first answer, right? Okay. Then it says how many joules of electrical energy can it produce in a 6-hour period when the sun is hitting the panels? Okay, so we're going to use this guy. Power is energy divided by time. So therefore, energy equals power times time. So that's going to be our 394.0475. That's important, right? And that's joules per second, right? And then it's a 6-hour period. So 6 hours times 3,600 seconds per hour. Okay, so take the number on my calculator, multiply by 6, multiply by 3,600. And that is, what is that? 8,511,426 joules, right? Or 8.51 megajoules, right? 8.51 megajoules, or 8.51 times 10 to the 6 joules, right? How many kilowatt hours of electricity is that? Well, we can just go with this. We can just use this conversion, right? Okay. A kilowatt hour is 1,000 watts for an hour, right? An hour is 3,600 seconds, so that's 3.6 times 10 to the third seconds. Kilo just makes that times 10 to the 3 more, which is times 10 to the 6th, right? So kilowatt hours is equal to joules divided by 3.6 times 10 to the 6th. This is joules per kilowatt hour. So if I take the number on my calculator, divide by 3.6 E6, that's only 2.36 kilowatt hours. Which doesn't seem like very much. It's like, oh, well, that's worth paying for, right? I mean, right? Like all that megajoules turns into kilowatts. A handful of kilowatt hours. All right.